here we are, page 8. This is from quiz 9. Sorry, which one did you ask for again, Kim?
5, so like that whole thing.
Oh, all of them. Okay, yeah, those are the reaction portions of the quiz. That'd be worth doing again. All right, so let's just tag the reactants to begin with. Here's your Rx. Here's the nucleophile. Any nucleophile has a lone pair of electrons on it somewhere. It may be positive, maybe negative or neutral. And by the way, the DNA in your body is the world's biggest nucleophile. So anything you learn about the little versions of molecules like that could also be true of the DNA in your body. So what you'll expect is that this nitrogen right here will end up on the carbon. And let me just see if I can keep this oriented the same as possible, as much as I can. So the ring, I guess I'd go ahead and draw like that. And then the new bond will be between the nucleophile, which is the nitrogen atom, and the R group. So you draw yourself a new bond. First of all, make sure that the nitrogen is in the ring where it starts out. Draw a new bond. You can draw it longer or shorter, just so long as it's clear that it's a bond. Then there's the R group on there. That would force then, of course, the nitrogen to have a formal positive charge on it. This is malfunction junction today. Okay, a positive charge there, and iodide would be an anion because it got knocked out as the leaving group. Okay, any questions about that? Now, because this is not a mechanism, you don't have to show lone pairs. The question just asks for a product, and that means that your lone pairs and other parts of a Lewis structure, they're not necessary. It's not wrong to put them in if you want to, but it's just extra stuff. Okay, let's see, McKenna, where you think you were the one who asked that? Good with that? Or?
I guess I'm confused about like how do you know whether you're going to substitute or if you're going to do like
elimination?
How do you pick which?
Okay, so your point is a good one. Clearly this is substitution. That's what happens. Why is it not elimination? And maybe that could be a little theme going through here, actually. Okay, why not elimination? Okay, to look at that possibility, what you're always starting with is the R group. You're asking the structure of the R group. Okay, so E, whether it's E1 or 2, that's going to require R is secondary or tertiary. All right, and that's the general pattern. And what do you see about this R group? Is it secondary or tertiary? It's not. So the only thing it knows how to do is substitution only. It's not just that it's primary, it's even smaller than that. This is methyl, so it's even smaller than secondary or primary or tertiary, what have you. It's not a candidate for elimination. All right, now that same discussion, though, would make sense on this next one. Is this one going to be substitution or elimination? Okay, so first of all, make your decision. Substitution, S or E. And you look at your R group, and you look at the other reactant, and you try to make a call. So here's Rx, and here's the nucleophile. And let's say what we can tell about each one of those just by checking it out and looking at it. Your R group, methyl, primary, secondary, tertiary. What would you call it?
Secondary.
It's secondary. Okay, and the nucleophile. And your decision is always, is it a powerful base? Yes or no? In this case, it is. It's hydroxide, so it's a really strong base. And so that combination is what tells you that this is not going to be a substitution. Not substitution. It's elimination, and I'll just briefly put a story here. Due to R being secondary, and the nucleophile is an extremely powerful base. You didn't learn very many of those. We're keeping the list pretty short. So what that's telling you is that you're going to have an elimination product. Both of them, here's what will tie them both together. Both of them will be alkenes. Both of them will be caused by elimination, not substitution. If you draw a substitution product there, no. This one's not a candidate for substitution. All right, the major product, how about if we get our carbon framework straight for both of them? That much is not going to change. So it makes sense to just draw how many carbons? 6 plus 1 off the ring. That's total 7 carbons. And just put your carbon framework in place to begin with. All right. Now you know for sure that the major product is going to be, of the two alkenes, more substituted. So you might just put that story here. This one is going to be more substituted because it's major. This one will be less. Okay, so the major product would need to be this one right here. Now, how do you know that? Well, you look at the carbon where the halogen starts out. That's this one here. It has the chlorine on it to start with. It can form an alkene going either side of itself. And the more substituted one, of course, is this one, because you end up with 2 partners there on that carbon, just 1 here, that's 3 partners. Whereas if you were to do it the other way, which I'm about to do in a minute, it has fewer partners. Each carbon has only 1. All right, but if it goes the other way, if it goes to the minor product, you've got your choice of hydrogens. Now remember, this is a regular hydrogen. This is just a hydrogen plus an extra neutron. But chemically, it doesn't know it's not hydrogen. It does the same thing. It does it slower, but it does the same thing. And the rule is that to eliminate your halogen, which is chlorine here, it's got to be able to line up 180 degrees trans from whatever hydrogen leaves on the neighbor. So this one right here needs a trans hydrogen in order to eliminate. So you're looking at these other 2 options here. These 2 characters are going, well, which one of these would be trans to it? Would it be the hydrogen or would it be the deuterium? So what's your call? Okay, the chlorine starts out pointing down, and it needs something in order to be trans that's pointing up, right? So these 2 are trans to each other. They are the ones that have to leave if an elimination happens at all. That means that the alkene forms there, and also the deuterium is gone. The deuterium is not part of the product. Would be another way to say that. If you can follow this one right here, you're following 2 or 3 things at once. One is recognizing substitution or elimination. Okay, so that was McKenna's question to begin with. Another thing you're doing is you're figuring out which is the major and which is the minor. So that's issue number 2. Elimination happens. What does it form? And then issue number 3 takes it clear down to the detail of not just which which spot will lose a hydrogen. It's which of the two hydrogens. This is nailing it down to just one level. Okay, I'm not sure what more to say there, so let's try to get your questions and work them in. Okay, go ahead.
You already explained it, but can you explain again how you use the alkene one on like which part, like major versus minor?
Yeah. Okay. The question is, how do you know which is major and which is minor? Focus on the two alkene carbons. They're both of them possibilities. Here's a partner and a partner on that carbon, and here's a partner on that carbon. Total 3. Then you go to this alkene here, and this carbon sees one partner, and that's all. And this carbon here sees one partner, and that's all. So this one is a so-called di-substituted alkene. This one's tri-substituted. If there were another carbon here, this one would be tetrasubstituted. You just got to draw your options. Whichever one is most substituted, that's major. Okay, more questions? Yeah.
The D isn't the one taken away in the major product, is it? Is it a different hydrogen? And
Let's
it's
see.
not drawn?
In the I should fill in the major product. The rest of it here. So yes, those are both still there. And let's see. I guess the deuterium is up, the hydrogen's down. Yeah, nothing happened here. Okay.
So the
go.
major product is always going to be more substituted?
Yes.
Okay.
Yes, it will.
Yeah. My copy?
So would there still be hydrogen sticking out on the minor product too?
Yeah, there is. Now, I didn't bother to draw it because it is only hydrogen. Okay, but it's not wrong to put it here. In fact, if you're really trying to communicate, hey, I've got only the hydrogen, not the deuterium, yeah, it makes sense to put it there. Okay, so again, the trick is to recognize the kind of reaction. So you're asking, what does my R group want to do? And what does my other reactant want to do? Once they agree, you're into elimination territory. Here's, I'm going to put this in really small drawing and point out what it isn't. Here's the urge. Everybody wants to do this. Right? Doesn't that look tempting? You take your nucleophile and you put it where the halogen used to be. So you just leave your other stuff where it was, and you're thinking only about substitution. I'm keeping that small on purpose. That's not what you want. That's substitution. Yeah, okay. Any more questions about that? Okay, remind me if I forget. I'll watch time goes. I want to give you another version of this question and see how you do it, recognizing it in a different form. Okay, but let's move on to what we are trying to get through. All right, you're looking at this. This is a product, and if I remember right, everybody did pretty well on this. It sure looks like this is a nucleophile on a carbon. Now, the rest of the stuff we can come back and fill in later, but it sure looks like there's a bond that got formed because something got displaced. Okay, this must mean that bromine was in your original Rx, and it sure looks like sodium, that looks like it was with the nucleophile. And so you're working backwards then, and it really doesn't matter which one you start with. How about if we just kind of keep things in the same order as they're drawn there in that product? So let's draw this piece, and then let's draw this piece, recognizing that to start with, each one of them had a different partner. They've ended up joined, But they weren't that way to start with. It was two separate reactants. And in order for you to have an Rx, perhaps the only debate here, the only possible trick, is to go, okay, I could put my bromine here with this ethyl group, but what if I put it here? Wouldn't that be just as right? And the answer is not really, because if you remember the formula for R, you don't want aromatic carbons right where the halogen is. So that's why you pick this one. This one is Rx. If you put the bromine over here, that would not be Rx. That'd be some other kind of X, but not willing to do substitution like what we're talking about here. So then it looks like the rest of it must have originally looked like this. Sodium, as always, would have a positive charge on it. The negative charge would have gone with sulfur. You could draw some lone pairs there if you wanted to, but this isn't a mechanism question, so you just stop with kind of the minimum. And let me emphasize this. It's not this. You wouldn't want to do this. So don't put your halogen there. And then what would the other piece of it have to, I guess the rest of it would have to look like this. Okay, those are dubious compounds anyway. Yeah.
So when it comes to these type of equations, is the nucleophile always leaving, or like how do you know which like gets replaced with which?
Yeah, the nucleophile is what comes in and it sits where the halogen used to be. So like what we drew right here, all of this piece right here, as we've got it drawn, that's the nucleophile. And it knocks out the bromine. So that's why over in the product version of it, you can eyeball it and go, that much of it must have come from my nucleophile. Okay, so any more questions on that one? Okay, next, let's do this last one at the bottom of the page. And the way the question is worded forces you to make the decision of SN1 or SN2. And it's given to you as it is. The question is about substitution, not elimination. All right, so that kind of simplifies things. And the unrearranged product is about the simplest one you can imagine. So you're just going to take your halogen and replace it with the nucleophile, and it would give you that. Okay, here's your X group, the iodine that goes away. In its place will be the nucleophile. Now that's kind of the, I guess you'd say, the easiest way you could envision it. The rearranged one is what will require you to remember something. Actually, I'm going to draw this down here below where it'll be bigger. Okay, the initial carbocation that forms had to form right here. Now this isn't a mechanism question, so let's not trick it out with extra details other than what we need. Remember that your charge in the carbocation forms here, and once that does happen, the carbocation is secondary. And that's okay. The structure that you're asked to complete in the first box says just give the product the way it would look at its simplest. No rearrangements, just do it. The next version, though, realizes that what could happen is that the carbocation could rearrange, and will, to some extent, rearrange to tertiary. Now something needs to move in order for that to happen. And so you can have a hydrogen move, you can have a carbon move. And I want to see if I can keep this oriented as much as possible the way it was. Okay, there's the framework. And here's what you got to look at. Right here, this one used to have 3 methyls. However, if anything can move, it will. So this one, now that it's rearranged, now has 2 methyls. It had only 1 to begin with. That's really the challenge right there. Getting the framework actually rearranged. That's what a rearrangement is. You've got a different framework. And so that's what happened here. Now, okay, let's not forget, put in the nucleophile. That one is where you've got to understand what a rearrangement means. Anytime something can start as secondary and go tertiary, or primary and go to secondary, if it can get more stable, it will find a way to do that. So here it is, drawn larger. Okay, we talked about rearrangements. I don't know that it's worth a lot of extra time here in the review, but that's what it'll do. Okay, let's see. That was the end of number 5, wasn't it? All right, we have, what else do we have on that one? There are a couple of mechanism questions, some multiple choice. Then, of course, there's the NMR material that starts out on page 1, goes for the first few pages there. So what would you like to see next? Are you both asking the same thing? They look at each other like, oh, I didn't know you were asking. Okay, so what are we going to do next? Number 4 on page 1? Page 9. Oh, that's from quiz 10, isn't it? Sorry, maybe you said that and I didn't hear. Could we wait on that one until Monday? Okay, please remind me of that, because, yeah, they'd all be worth looking at. And if, what was the other one?
Could we do number 9 on page 2?
Number 9, page 2. Yeah, okay, so this is starting you off with a spectrum, and you need to map signals to a structure. Okay, how about if I do number 8 as well, so we can kind of eliminate answers as we go. By the time we get to 9, it'll be a little easier. Okay, so we've got 1, 2, 3, 4, 5 sets of hydrogens there, and you're asked to map each one to a signal here. The B hydrogens, and it might be easiest to start by saying, well, what kind of splitting would you expect out of that signal? The B hydrogens. And so let's put a quick term on it, things like doublet, triplet, quartet, whatever it would be. The B hydrogen should be a what? It should be a triplet, yeah. And the reason for that is that as they look around at the world, they look to their left. And they see a carbon that has 0 hydrogens, so no neighboring hydrogens there. They look the other way and they see 2. 2 plus 1 would be 3. Okay, the B hydrogen should be a triplet. You go to your spectrum and you look for triplets, and there's 1, there are 2.5. That's a singlet. That's more than a triplet, both of those. And there's a triplet. Okay, if you're looking at a triplet, you're saying, well, it's seeing 2 hydrogens. It looks like this one right here, the E hydrogens, also should be a triplet. So we've kind of got our choices sorted out for us here already. Both B and E should be triplets, and there's only 2 signals here. Now you've got to kind of narrow it down, sort out which one goes with which signal. One of these, this one here at 2.5, is way downfield compared to the other. It means left. That means it's feeling more competition for the electrons that share around it. It suggests that there's an electron withdrawing group closer to this one than to this one, and so I guess that would be worth putting as text on your figure. This one's closer to an electron withdrawing group. All right, so look at your structure then, and you're going, which one, B or E, should be closer to an electron withdrawing group? And which would you say? The farthest downfield one, would you say that's B or is it E? Yeah, this one's B. And you could even put specific things here by saying that this one is closer to that group where oxygen is part of the mix. That leaves E for this one right here. So finally we got to number 9, which was your original question. Okay, questions on that or others?
I do have a continued question. Okay, so when you're looking to determine whether it's a triplet or is the singlet?
Mm-hmm. There's the singlet right there.
Okay, are you looking at like the number that's by the hydrogen, or are you looking at like the neighboring groups?
It's the neighbors.
Okay.
Here's the urge. The urge is to look at this group out here, group E, and say there are 3 hydrogens in it, therefore it should be a triplet. Okay, I've watched that pitfall happen a number of times. So that's not what you want. It is a triplet, but it's triplet because it has 2 neighbors, not because it has 3 hydrogens within itself. The splitting is determined by the neighbors. You could have lots and lots of hydrogens here. They don't care if they're all the same thing. They only care about their neighbors when it comes to splitting. Yes, ma'am.
That could you go on page 1, number 3?
Okay.
Would it be B or A for which one's better?
Okay. Your question is about number 3. Okay, so here's the structure. And the question would be, which one should appear farthest downfield? Okay, so there are 2 candidates for that, I would say. And here's one of them. And here's the other one. So this first one is near an oxygen. This next one is near a chlorine. Both of those are heavy-duty electron thieves. Yes.
How come it wouldn't be B? Like one of the options?
This one right here.
Yeah.
Okay. This one is actually. Let me work that in. This one is near to a carbon with a double bond on it. So yeah, you could kind of say that one's a candidate. The reason for focusing in on A and C is that the hydrogens you're looking at are on a carbon where the carbon itself has this tough partner, either oxygen or chlorine. This set right here, set B, yeah, it does feel some electron withdrawing, but it's actually sitting on a carbon, and then that carbon is the one that's bearing the real brunt. Another way to count it is to say, from this carbon where these hydrogens sit, you go through 2 bonds to get to the real electron thief. And this one right here, you go through only 1 bond. The carbon is bound directly to the oxygen, and same goes on the other end of the molecule. That one's bound directly to chlorine. the closer the element is, the more damage it does. All right, which one should be farthest downfield? Well, oxygen is more electronegative than chlorine. You can get that from a number or look at where it sits in the table or something. Oxygen is more electronegative than chlorine. So I guess I would expect A to be the farthest downfield. So if you're circling the carbon, the signal should have... Oh, that's a carbon-13 question. I'm sorry. Here I am answering it for proton NMR. No wonder you asked the question. Okay, sorry. Let me go ahead and add that in, though, but let's answer the real question. So this carbon right here actually feels two electronegative elements. So the carbon-13 signal is farthest downfield. If the question had been for proton NMR, the story I started out telling would have been right, but let's stick with the actual question. So it's the carbonyl, which looks like this. It actually is bound to two different electronegative groups. Okay, it took me a while to get there, Naya, but I think I kind of got there. Any others? Yeah, the first question, number 3, was about a carbon-13 signal. The rest of them are about proton signals, and I don't remember any major problems anybody had with those. If you had a question, we could certainly look at it. That's probably not the top priority. Okay, we've done some NMR here. Oh, we do have these questions on quiz 8 that deal with thermodynamics. I don't recall any major glitches with those, but are there a few individual ones that stand out? Okay. Yeah.
7 and 8 on page 5.
7 and 8. Okay. This one was based off of homework, so hopefully it wasn't too obscure, but let's look at it. 7 and 8. We're looking at the reaction in the box, and what you're seeing here is just a reaction. You have two reactants over here. We'll get to this in the next chapter, by the way. Two reactants go to make one product, and that really is the only information you have to help you make the call here at number 7. And if that's all the information you have, you're going, well, the product, since there's only one of them, is less disordered than the reactants. If you started out with 100 molecules of reactants, so like 50 of each, you'd have 100 molecules of reactant, you'd end up with only 50 molecules of product. Well, there's less stuff flying around randomly in there. That means that since it's less disordered, the value of delta S should be negative. Negative means less random, less disordered, and so forth. And the reason, well, I already kind of wrote the reason here. There's less disorder in the products than in the reactants. All right, we better wrap up here in the next few minutes pretty soon, because I think there's some quizzes downstairs that some of you left. I didn't pick them up. I'll make sure that I get down there early enough before the next class to do that. But if there's like just one other quick thing, we could do that and then pick up again.
9 too.
9, okay. So delta H equals, delta G equals delta H minus T delta S. There's the story. And what you're told is that the delta H value is really negative and the delta S is positive. Okay, so what that must mean is delta G is way negative. And let's see what statements match here. The reaction is non-spontaneous. Nope. It's definitely spontaneous. That's what a negative delta G means. It does want to happen all on its own. The reaction is endothermic. No. Delta H, endothermic just refers to the heat part, so that's delta H. Delta H is negative. It releases heat, and we're told that. Delta G is negative. Yes, that's for sure. Equilibrium constant is smaller than 1. No. If you have a negative delta G, that's a statement, that's a warning for you. It means that the equilibrium constant is greater than 1, way greater than 1. So that just leaves C, it looks like. All right, why don't we call it good for there? We'll pick up and do more on Monday. Those of you who came in and have quizzes here in this room, how about putting them front and center on this bench? I'll get the other group from downstairs.